All right, thank you very much. So my research starts out with a problem statement, and the problem is TCE, or trichloroethylene. So this is a really common groundwater carcinogen pollutant distributed across the industrialized world. So TCE was used as a degreasing agent and as a dry cleaning solvent from the 1920s to the 1980s. But it turns out it's very carcinogenic at low concentrations. So the EPA limit for drinking water of TCE is 5 parts per billion. That's the equivalent of a mouthwash cap full of TCE dissolved in an Olympic-sized swimming pool. So little TCE goes a long way. The way it's currently treated, so TCE is heavier than water, so it sinks down through the aquifer when it's spilled. And our current approach to this is to pump bacteria, a special kind of bacteria, dehalogenators, into the aquifer, and they degrade TCE. The problem with this is that TCE is degraded sequentially with intermediate byproducts. So the bacteria degrade TCE to DCE, and then when they run out of TCE, they switch gears and start degrading DCE. At that point, they run out of DC and start creating VC. So it's a sequential hop. So we see a TCE plume turns into DC plume, turns into a VC plume. And the problem is VC, the second to last product, is twice as toxic as TCE. So if we don't go all the way, we actually make things worse. The second problem here is that every time the bacteria make one of these degrading steps, they release acid. And many times bacteria can acidify themselves to death. And if that happens, you're probably going to be left with a big plume of VC and you've made things worse instead of better. So our solution to this problem is to put the bacteria into an artificial biofilm, or a hydrogel. So this is basically a gummy bear, but instead of being made of gelatin, it's made of PVA, polyvinyl alcohol, and sodium alginate. So polyvinyl alcohol is essentially Elmer's glue, and sodium alginate is a seaweed extract, so it's biofriendly materials we're using here. So we've seen in our lab modeling and testing a lot of benefits to putting bacteria into these gels instead of just directly injecting them into groundwater. So one of the big takeaways is you have a sphere of a biobead, and TCE diffuses into it. Now the bacteria at the surface degrade TCE. As it moves further in, the DC moves further in, and the bacteria degrade that. At the center, there's no TC and no DC, so bacteria degrade VC. So we get simultaneous degradation all at once. Another benefit to this is the sodium alginate in the membranes, the seaweed extract, absorbs free protons, so it soaks up acid. So what we end up having is a biobead degrading all these carcinogens at the same time and absorbing the acid as it goes along, keeping the bacteria at a nice pH and maintaining their growth. So a final thing we've seen that we didn't expect going into this project was that TCA diffuses very fast through these membranes, but VC diffuses 3 times slower, which is amazing because the most toxic compound we have in the system spends the longest amount of time in the bead, giving bacteria plenty of time to degrade it. Thank you all very much.